This is my fifth lecture on related to analog electronics. Today's lecture is on feedback topologies and also on oscillators. Now, the last 4 lectures which I had, most of them were concerned about amplifiers. Now, what in all those cases we did not much worry about feedback, or most of the time the amplifiers which we considered had no feedback. Now, feedback as a concept is an extremely important concept. Now, we are all familiar with it in our everyday life. The concept of feedback is extremely important in all fields of engineering. Now, there is not a single field of engineering which does not use the basic concept of feedback. Now, most of the time when we talk about feedback, we actually mean negative feedback. So, generally, just like when we say amplifier, we generally mean voltage amplifier. Similarly, when we talk about feedback, we kind of assume that we are talking about negative feedback. Now, why is feedback used? Now, feedback is used to make sure that the quantity of interest to us is stable, and it stays stable irrespective of small disturbances. Now, in our context, we are talking about amplifiers. So, therefore, most of the time we are interested in getting a stable voltage gain. When you did the experiment on the BJT amplifier, I am sure that there would have been considerable difference in the actual voltage gain you would have got. Maybe within the same remote center, maybe the 10 people, if you had compared the gain, there would be at least about 1% variation, or sometimes even more than that. Now, this is because of the reason that the common emitter amplifier which you used did not use any feedback. In fact, the second part of the common emitter amplifier, you had negative feedback, and in that case almost all of you would have got almost exactly the same gain, irrespective of what gain you got in the same amplifier without feedback. So, you have already seen the use of feedback, and you have some practical exposure to it in the context of amplifiers. Now, it is not just engineering where we use the concept of feedback. If you look at our human body, we use negative feedback very extensively. Now, think of the, say, a simple example of lifting an object. Let us say that you want to lift a, let us say, a notebook, or let us say a textbook. Now, before you even touch that textbook, your eye would kind of make an estimate about the weight of that particular book, and then your hand goes there and touches it, and the brain has already instructed the hand roughly the weight of the book. But when you touched the book, it was either lighter than what it was computed, or it was more than that. So, accordingly, the brain would immediately activate things. Similarly, when you climb a staircase, I am sure occasionally when the staircase size, the step height is not same, very often we all fall down, either where you are coming down. Most of the time, if you are coming down the stairs, and if it so happens that one of the staircase steps is slightly having, say, less or more height, then you would almost will fall. Why is it so? Because at the first instant when you stepped on the staircase, your brain had an approximate idea. When you put the first step, it immediately calculated the amount of length by which your right leg or the leg left leg should move. Now the second step, that approximation whatever it did was even made perfect. After 2-3 steps your system has adjusted very well, and without even you looking at it you can go down. But if it by any chance if the last step happens to be either having smaller step height or higher step height, we would almost all of us would fall, or you would have a bad hit on our leg. So we see that our body extensively uses feedback. Now another very good example is our sense of hearing. Now maybe you could try this experiment. You could just talk to sometime maybe to your friend normally, and then try to do this by putting an earphone into your ear. Now if you do that, you would see that you will automatically use much louder sound than what you use without putting something in your ear. Why is it so? Because when we speak, our ear gets a feedback. Now based on that, the ear makes an estimation whether we are loud enough or not. If we are not loud enough, then we would speak louder automatically. So we see that we have the concept of negative feedback is extensive, and it is there almost in any field, and it is not just limited to engineering. But we shall talk in the context of using negative feedback for amplifiers. So we would limit it to that. Now when you talk about feedback, there are two types of feedback. Now the one which we would use in an amplifier is what is called negative feedback, or it is also called degenerative feedback, and this is the one which is used extensively in amplifiers. The op-amp amplifiers which we are familiar with, they all use negative feedback. Now you also have positive feedback, and very seldom we come across positive feedback, but in today's lecture we will talk about both negative feedback and positive feedback. We would spend more time on negative feedback, and towards the end of the lecture we will talk, in the context of oscillators, we will talk about positive feedback. Now positive feedback, very often is thought that it is something to be avoided, or very often we might think that maybe positive feedback should be used only for, let us say, oscillators, sine wave oscillators. But interestingly, positive feedback is very useful in wave shaping circuits. Positive feedback is very useful. I am sure you are all familiar with op-amp based comparators and op-amp based Schmitt trigger. Now what is the difference? What is the major difference? Both of them would compare the input and give you an output. Now we know that the Schmitt trigger has a certain level of hysteresis. Now in addition to that, another very important property of the Schmitt trigger is that it uses positive feedback to give you an output which is much sharper than what you would have otherwise got from a comparator. Now what positive feedback does in the Schmitt trigger is that as soon as you cross either the upper triggering point or the lower triggering point, the output would either go high or low depending on your configuration. Now the output would rise as fast as it can, whereas in the case of a comparator, even if you have a certain level, even if you cross that level, now since a comparator is used in an open loop mode, there is a small region which is a linear region, because of which the output will not rise fast as it does in a Schmitt trigger. So we see that positive feedback is also very useful, and it is used again extensively in electronic circuits. So we shall discuss both of them. Now what I have here is a kind of general structure of the negative feedback amplifier, a very similar structure is also very often used in control systems, maybe one of the first things to do in a control system course. Now, so the basic block diagram which is shown here essentially gives you an idea about negative feedback and how it is applied in an amplifier. Now, we have a voltage source whose output, let us say, is Xs. Now, Xs may be either current or voltage. Now, this needs to be amplified in an amplifier. So, we have an amplifier which has a gain of A. Now, the output of the amplifier is X0 or XO, and that is applied to the load. Now, in a negative feedback amplifier, what you would do is you would take a sample of the output, and a sample of the output is then fed back to the input, and at the input it is summed, rather it is subtracted from the source value and then applied to the input. Now, because of this kind of a subtraction at the input point, we call it degenerative or negative feedback. So, we see in this case we have two directions. One direction, the signal flows from the source through the amplifier to the load, that is one direction. Now, side by side we have another direction, the signal flows from the output through the feedback network back to the input into a summer, where it is subtracted, proportionately it is subtracted from the input and then fed to the amplifier. Now, if we write this in terms of equations, we have just simple three equations from which from these equations we can get an expression for the voltage or the current or just gain with feedback. Now, the output, let us say parameter X0, we know is related to the input parameter Xi by the gain. So, we can write a simple equation as XO is equal to A times Xi. So, that is the first equation we have. So, that is always valid. Now, the second equation relates the feedback, the quantity of feedback. So, what is done here is we take a sample of the output and a certain proportion of it is fed to the input. So, this XF parameter is related, it is like something like a, let us say, a gain parameter of the feedback network. So, XF is equal to beta times X0, and again a very simple equation. Now, the third equation we have relates to the way the signal is added at the input. Now, we see from the diagram that Xi is nothing but Xs minus Xf. So, that is the third equation. Now, if we use these three equations and we, for example, write an expression for XO by Xs. So, XO by Xs, which we will define as the gain with feedback AF. We would see that you can write the expression for a X0 as A times Xi, and Xs we can write as Xi plus Xf, and then we can express Xf in terms of Xi, and then we would get the simple expression that AF is equal to A by 1 plus A beta. Now, this is an expression which is used extensively in many areas. Let us try to understand what this particular expression means. So, what we are saying is the closed loop gain, that means the gain which we are going to get with feedback AF is equal to the gain which was there without feedback divided by 1 plus A beta, where beta is the amount, say the proportion or the gain parameter of the feedback network. Now, the term A beta is called the loop gain, and we see that this particular A beta is an extremely important parameter, especially when we talk about oscillators. We would see this is a very important parameter. Now the denominator 1 plus A beta is called the amount of feedback, and again we would see this term 1 plus A beta coming repeatedly again and again, we will see later. So 1 plus A beta is called the amount of feedback and A beta is called the loop gain. Now one very important thing which we need to assume in all our discussions is that the loop gain A beta must be positive for the feedback to be negative, otherwise all that we did will not be valid. Now the gain with feedback AF, we see that is smaller than the open loop gain by the quantity 1 plus A beta. So before applying negative feedback we had A as the gain. Now after applying negative feedback, the overall gain reduced from A to A by 1 plus A beta. So we see that this is one of the most important say features or the, let us say, the peculiarity of negative feedback. Now in negative feedback we always trade gain, the open loop gain, with the other parameters of interest. Now we will again discuss this particular topic, this particular peculiarity or the feature of all negative feedback amplifiers. Now the price we are paying here is the reduction in the gain, but we will see that, we will see soon that we get many things in return. As we all know, in engineering, in any design, not in any design, there is always a trade off. We never get all that we want. We saw that even in the previous lecture where we talked about multi-stage amplifiers. We said that we never have a, let us say, the ideal single stage amplifier. So to construct an amplifier for an application, we try to put different non-ideal amplifiers in such a way that we get something what we want. So trade-off is something which we are very familiar in engineering. Now another very interesting thing to note here is that AF is equal to A by 1 plus A beta. Now if A happens to be extremely high, let us say much greater than, let us say, 1000, then we see that this closed loop gain AF will be approximately equal to 1 by beta. Now this is something we are very familiar with. We will talk about this later. When we, in the case of an op amp, where we would see the same equation again coming. Now in the case of an op amp, this quantity A, the open loop gain, is of the order of 2 into 10 power 5, extremely high. This is precisely why we in a op amp amplifier, say non-inverting amplifier, we can get an expression for the closed loop feedback independent. So one very important observation regarding what we written here is that if the open loop gain is large, A is large, the closed loop gain AF depends only on the feedback network. Now this is an extremely important property, an extremely important feature of negative feedback amplifiers. So if we want to make our closed loop gain independent of the amplifier, all that we need to do is to increase the overall gain. So in any design, in the design of a negative feedback amplifier, this is a very important consideration, to keep the open loop gain very high, so that when you apply negative feedback, the parameter of interest gets stabilized very well. Another very interesting observation is that since our AF is now only dependent on beta, which is the feedback parameter, we can say that we said as right now that the gain depends only on the feedback parameter. Now in the case of an amplifier, this feedback network we have is made of only resistors. Now therefore we can make the gain dependent only on the resistors which we are going to put. Now we know that, assume that you have a very precise application where you are very particular about a particular gain value. And in such an application, just by choosing say precision resistors, you could easily attain the closed loop gain, and that would remain stable irrespective of, even if you change the op amp say tomorrow, you would see that the closed loop gain depends only on the resistors which you have used in the feedback network. So this is an extremely important observation and an extremely important feature of negative feedback. Now let us look at the kind of advantages of negative feedback. Why should we use negative feedback? Let us see them in a bit detail. Now one of the first things we talk about when we talk about negative feedback is the gain desensitivity. What we mean by this is, if you differentiate the expression for AF with respect to A, you would see dAF is equal to dA by 1 plus A beta the whole square. Now then if you write dAF by AF, you would see that you will see that it is equal to 1 by 1 plus A beta square times dA by A. Now what this particular expression is telling us is that the percentage change in AF is much smaller than the percentage change in A, and it is related by the amount of feedback. So for example, if your A, the open loop gain, let us say changes by 50%, or let us say it gets doubled or it gets halved. Now the effect of that open loop gain on the closed loop gain is determined by, it will be only by that change divided by 1 plus A beta. Now this is an extremely important feature to be kept in mind, and this is one of the major advantages which we just now talked about. We said that that in a negative feedback amplifier, we said the closed loop gain, provided the open loop gain is above a certain particular value, the closed loop gain does not depend much on the open loop gain. So gain desensitivity is an extremely important advantage of negative feedback. Now another very useful and advantage of negative feedback, and very often negative feedback is used for this purpose, is that by applying negative feedback the bandwidth would get expanded, or we can say that we get a extension in the bandwidth by applying feedback. Now if like the amplifier, let us say the common emitter amplifier, if we assume the high frequency response to be characterized by a single pole, which is a very good approximation, we can write the response as AS is equal to AM by 1 plus S by omega H, where AM is the midband gain. We talked about midband gain. We said midband gain is the region where the gain is steady, and we said in a common emitter amplifier, we said this is a region where the coupling capacitors can be considered as short circuits, whereas the device capacitors can be considered open circuit. So AM is the midband gain and omega H is the upper 3 dB frequency. Now by applying feedback, we can show that the upper 3 dB frequency gets extended by 1 plus AM beta. Now this is extremely high. Now this can be easily proved, and one of the best ways to prove this is from the example of a non-inverting amplifier, and I hope we are all familiar with this, with it. Now we talk about the gain bandwidth product being a constant. Now we would see that in a non-inverting amplifier, we see that by applying feedback, we would see that the bandwidth or the upper cutoff frequency increases by the factor 1 plus A beta. So this is an extremely important use or advantage of negative feedback, and very often we use negative feedback to get higher bandwidth. There are two more advantages which may not be that important, but there are applications where this may be important. Now, negative feedback can reduce the noise in an amplifier. What we mean is by that is it can increase the signal to noise ratio of that amplifier. So basically what we are saying is, by using negative feedback we can reduce the effect of noise generated in an amplifier. Now we should be very careful when we talk about noise reduction. Don't confuse this with as though saying that if your input signal is corrupted, let us say with noise, by passing it through a negative feedback amplifier, that noise, whatever signal to noise ratio which you have at the input of an amplifier, cannot be improved. So that is not what we are talking about. What we are talking about is, if the amplifier which you have has, let us say, it generates noise internally. Now by applying negative feedback you can reduce the noise generated within that amplifier, so that the overall signal to noise ratio would be much better than what it would have been without applying that feedback. That is the meaning what we are trying to say about noise reduction. So this must be very carefully, the distinction must be very carefully understood. Now another occasionally another common application or advantage of negative feedback is that the nonlinear distortion can be drastically reduced. Now we all know that a BJT is actually a nonlinear device, and we said when we talked about common emitter amplifier 2 lectures ago, we said that we have what is called a small signal approximation. We said that we need to keep the signal, the AC signal, much smaller. We said within about 10 millivolt or so. Otherwise we said we would get distortion, and that would make the output kind of nonlinear. You would get distorted output. Now by applying negative feedback, this range can be drastically improved. So an amplifier, if it had some amount of tolerance, by applying to, let us say, nonlinearity, by applying negative feedback you can increase that range, which means it can now tolerate more, nonlinearity. So this is again an important application when we talk about say in the context of nonlinear distortion. So we talked about 4 major advantages of negative feedback. We talked about gain desensitivity, we talked about the bandwidth extension, and then we talked about the noise reduction, and finally we talked about reduction in nonlinear distortion. Now let us talk about the basic feedback topologies. Now this is where we need to go slowly. Now we know that we have 4 types of amplifiers. We talked about that again when we talked about common emitter amplifier. We talked about 4 types of amplifiers. We said that we have voltage amplifiers, we have current amplifiers, we have transconductance amplifiers, and we also have trans resistance amplifiers. Now there are 4 feedback topologies, in fact catering to each of these 4 amplifier types. Now these 4 feedback topologies essentially depend on 2 things. One, it depends on the parameter to be amplified. Now we know the parameter to be amplified, it may be a voltage or it may be a current. Now the topology also would depend on the output parameter. Now whether it is a voltage or a current. Now each topology is characterized by the connection at the input and at the output. So let us look at them in some detail. So let us name them one by one. Now this is where we need to go slow. I will repeat it again. This is where we need to understand this very well, especially even if you do not remember all these names, at least you should be able to say how to arrive at these names which you are given. So you need not memorize these names, but you should very well know how did we arrive at these names, then it's okay. So let's look at them one by one. Now the first of the feedback topologies is what is called a series shunt feedback. Now it's also called voltage mixing, voltage sampling. Now this kind of a feedback topology is suitable for voltage amplifiers. Now it's very evident from the second name we gave here that this particular feedback topology is actually meant for voltage amplifier. We know that in a voltage amplifier both input and output are both voltages. Therefore, whatever we are going to mix at the input of the amplifier is definitely a voltage, and what you are going to sample at the output is also a voltage. So this we will see why it is called series shunt feedback, but at the moment we can say that this feedback is called voltage mixing, voltage sampling, and it is suitable for voltage amplifiers. Now the second topology is called shunt series feedback, or a name to understand from its application is current mixing, current sampling. Now again it is very evident from this second name which we gave, current mixing, current sampling, that both input and output parameter, both of them are currents. Therefore we know very well such an amplifier is nothing but a current amplifier. So this is the topology which is useful for a current amplifier. Now you could immediately notice something interesting here. The voltage amplifier is called a series shunt, whereas a current amplifier with feedback is called shunt series. We will see why. Let us go to the third one. Now the third one is called series feedback, or the other name is voltage mixing, current sampling. Now again, just like the way we argued in the previous case, this particular feedback is suitable for transconductance amplifier. Now we know that in a transconductance amplifier the input is a voltage, whereas the output is a current. Therefore this second name we understand very well. We have voltage at the input, therefore it has to be a voltage mixing, because mixing we do at the input. The output is a current, therefore what we sample must be current, therefore it is current sampling. So this second name which we have given is a very easy way to understand what is being done, and from that we will derive the other name. So this is called series feedback, or voltage mixing, current sampling. Now the final feedback topology is what is called shunt feedback. Again you can see it's very interesting, series, this is shunt. Now here this is also called current mixing, voltage sampling. Now again we see that why it is called current mixing, voltage sampling, because we know that this is suitable for the fourth type of amplifier which we are familiar with, which is the trans resistance amplifier. We know that in a trans resistance amplifier the input to the amplifier is a current, therefore we must be mixing only current. Now a trans resistance amplifier, the output is a voltage, therefore we sample voltage. So it is very easy to understand what the topology is from the second name we are given. So once again, to quickly recap, we have four types. The first type is called series shunt feedback, or voltage mixing, voltage sampling, and this particular feedback is suitable for voltage amplifiers. The second one is called shunt series feedback, also called current mixing, current sampling, and it is actually suitable for current amplifiers because we are actually both input and output parameters are current. In the case of a series feedback, we said that it is meant for a transconductance amplifier, and we know that in a transconductance amplifier the input is a voltage, the output is a current. So therefore we mix a voltage at the input, we sample a current at the output. Now finally we have the shunt feedback, which is a current mixing, voltage sampling, and this is suitable for trans resistance, and we know that in a trans resistance amplifier The input is a current, therefore, we need to mix current at the input. The output is a voltage, therefore, we should be sampling voltage. So, the second name is something which is extremely useful to keep it in mind. So, even if you forget the first name, if you can remember the second name, you can easily arrive at the first one. Now, let us see each of these topologies in detail. So, let us see this in detail. What we have here is the block diagram of an ideal series shunt feedback, and we said the other name for a series shunt feedback is voltage mixing, voltage sampling, and we also said it is meant for voltage amplifiers. Now, let us look at the scheme here, the block schematic here. You have an input which is a voltage source Vs here. Now, that is applied to the voltage amplifier. Now, we can see a mixing done here. So, a fraction of the output voltage again is sampled using the feedback network, and that voltage is added in series. Okay. We have to always add voltage in series. This is a very basic concept as far as voltage is concerned. We can never connect two voltages in parallel. If we do that, I mean, there is nothing there. So, that is a very basic thing. So, this is another very easy thing to remember, that if you are talking about a voltage, then if you want to alter that voltage, you can only alter it by adding or subtracting. You cannot alter it by connecting a voltage in parallel. So, this is why the feedback voltage is subtracted and then fed into the amplifier. So, now let us come and understand why it is called series shunt feedback. So, we see that at the input side we have a series connection. We have a series connection, and we said why it is series, because we need to add or rather subtract the feedback voltage Vf from the input voltage. So, our Vi is nothing but Vs minus Vf, the way the polarity also indicates that. So, therefore, this is called a series connection. So, the first term there indicates the way it is mixed. So, the mixing at the input being a voltage is series, therefore, it is called the first word series there. Let us look at the output. Now, we know that if I want to measure a voltage using a multimeter, I measure it by connecting two terminals across the terminals of the voltage source. So, if I want to sample, then I have to sample it not by connecting something in series, but by measuring it across the source. Therefore, we have a shunt connection or a parallel connection. So, if I want to sample a voltage, therefore, I always need to sample that voltage by a parallel connection or a shunt connection. So, now we understand why these two words have come. Series word has come because we are mixing the voltage in series at the input. The word shunt has come because we are sampling the output parameter in shunt, and we said that if you want to sample a voltage, then you have to do that by tapping it across. Mind you, by doing this, we don't want, in the ideal case, we don't want to disturb what is going on. So, this is just like in a multimeter, if you want to measure a voltage, by measuring a voltage, you are not upsetting the rest of the network. So, that is the way you sample. So, therefore, the word series shunt, a series mixing at the input, a shunt sampling at the output. So, now it is very clear, voltage mixing, therefore, is called series, a voltage sampling, therefore, is called shunt. So, even if you forget this word series shunt, it is okay, as long as you remember that whenever we mix a voltage, we need to do that in series. Whenever we sample a voltage, it has to be done in parallel. Now, let us look at the next topology. Now, this topology, the name we gave is shunt series feedback. Now, we said the name is also current mixing, current sampling, and we said it is meant for current amplifier. Let us look at the overall amplifier in detail. So, we have a current source here, Is, and it is shown here in its Norton equivalent circuit. So, you have an Rs here, which is the output resistance of the current source. Now, we know that essentially what we want to do, the current flowing into the amplifier must be the source current, and from that we need to subtract a certain amount of current. Just like in the case of voltage, the previous case of voltage amplifier, we subtracted a certain amount of feedback voltage from the source voltage to get the input to the voltage. Similarly here, the input is Is, we need to subtract some amount of current which is If here, and the Is minus If is Ii flows into the amplifier. Now again conceptually think about a current. Now if I want to change a current, I can never do that by connecting in series, that will be absurd. Now I can only change a current by tapping, rather, let us say that I have a load connected, you have a current source and is connected to some load. If I want to change the current flowing into the load, I can change it by connecting something in parallel to that load and tap away or just kind of shunt away some amount of current. This is precisely why the word shunt is coming here. Since we are mixing a current here, we can do, conceptually you can never mix current in series. If you want to do a mixing of current, it has to be done in shunt. Therefore the word shunt here. Similarly, we need to sample a current. Now how do we sample a current? Now if I want to measure a current, we all know it very well. If I want to measure a current, we have to connect the ammeter in series with the circuit, not in parallel. We measure voltage by connecting in parallel, but if we want to measure current, we connect the ammeter in series. So same way here also, if we want to sample the current, then we must have a series connection. You have some network which samples maybe a proportion of that current. So therefore we have a series connection at the output because we are sampling a current, extremely important. So when I sample a current, think about an ammeter. Similarly, when you sample a voltage, think about voltmeter. So a voltmeter, we connect the terminals in parallel, therefore you have a shunt connection there. A current, if you want to measure or sample, I have to do that by connecting a meter in series. So that's the way you can think about, therefore I have a series connection. Therefore the name here makes sense. Mixing is current, therefore I have the word shunt. Now the sampling of current is done in series, just like in an ammeter, therefore the word series. So shunt series feedback is it's primarily meant for a current amplifier. So I hope these names which we are given there makes some sense. Now coming to the third type of feedback topology, this is called as series feedback or voltage mixing, current sampling. Again let's now we can understand, since we have discussed the other two, these two names would be fairly simple. Now we know that in a transconductance amplifier, the input signal is a voltage. So what do we have here? We have a voltage source connected to the transconductance amplifier. Now if we did not have a feedback, we would have connected this particular terminal directly to the transconductance amplifier. Now because of the feedback, we have introduced a certain voltage in series, and we said if I want to subtract something from a voltage, I have to do that in series, not in parallel. Conceptually that is absurd. So therefore I have a series connection at the input because I have a voltage signal. So therefore the word series here, because I have an input parameter which is a voltage. Now the output in a transconductance amplifier we know is current. Now we know immediately that if I want to sample a current, I have to connect the ammeter in series. In this case the feedback network must be therefore in series. So therefore I have a series connection at the output. Now again coming back, so we have a series feedback because we are mixing a voltage, and we said voltage has to be mixed only in series, therefore the word series. Now we are sampling a current, and we said current can be sampled only serially, the way we connect an ammeter. So therefore the word series feedback. And now I think it makes a lot of sense that for the transconductance parameter, with feedback, the feedback topology we would call it series feedback. Now we are left with the last topology, which I am sure you can mentally argue it yourself why this particular name, shunt feedback. Mind you, this is a trans resistance amplifier, therefore we are talking about a current at the input. So essentially our input parameter is a current. Now if we did not have the feedback network, we would have connected this directly and we would not have had these two wires here. So the output is a voltage. Now since the input is a current, if I want to subtract something from that input current, I have to do that in parallel, and we said that very clearly, because changing a current by a series connection is absurd. It does not make any sense. It has to be done in parallel. Conceptually, that is the only way you can do it. Therefore the word shunt. Now here the output is a voltage, and we said that if you want to sample a voltage, we sample it like we measure a voltage with a multimeter or a voltmeter. So we need to measure or sample in parallel for shunt. Therefore the word shunt feedback. Again, just to just brush it just quickly once again, these 4 topologies. So I hope next time when you hear these words, at least it will not be too complicated. Now feedback, unfortunately, feedback topologies, feedback amplifiers are dreaded by everybody, definitely by students. It's something which is supposed to be very tough and something which nobody can understand, but actually it's not that difficult if you look at it carefully and tries to understand it from a basic point of view or a conceptual point of view. So quickly again to recap what we discussed, we have 4 feedback topologies. We have a series shunt feedback meant for a voltage amplifier. So if I have a voltage amplifier, I have to use a series shunt feedback. Why? Because I need to mix a voltage at the input, and I can mix voltage only by a series connection, not by a parallel connection. Now being a voltage amplifier, my output parameter is a voltage, and I sample a voltage like I measure voltage with a multimeter or a voltmeter, and that has been done in parallel. Therefore I have a series shunt feedback for a voltage amplifier. Now coming to a current amplifier, I need to mix current at the input, and I can do that only by connecting a shunt connection. Therefore I have a word shunt here. Now being a current amplifier, I need to sample the current at the output, and we need to sample it like the way we measure a current using a multimeter or an ammeter. We connect an ammeter to measure a current by connecting it in series with the circuit. Therefore you have a series connection. Therefore the word shunt series here, or current mixing, current sampling. Now the third category of the amplifier is a transconductance amplifier. Now the feedback appropriate for this particular amplifier is the series feedback. Why? Because input parameter is a voltage, therefore we need to add or subtract the feedback voltage in series. Therefore we use the word series here. Now the output is a current, and my current sampling needs to be done in series, therefore the word series. So series feedback is the topology to be used for a transconductance amplifier. Coming to the last topology, we have a shunt feedback, which is meant for trans resistance amplifier. Now in a trans resistance amplifier, my input is current. Now therefore mixing has to be done in shunt, therefore the word shunt here. Now the output is a voltage. Now a voltage I sample in parallel the way I do with a voltmeter, therefore the word shunt feedback. So I hope to some extent these names make sense now.